So let's start with which are the major components of MAZESOLVING robot. The whole system can be divided into three major parts. First one is hardware, second is sensor and telemetry, and final is algorithm. What I'll do is I will share my experience with each part and the component which falls under these major parts in detail. So let's start with hardware. First component of hardware is chassis or frame. It is rigid structure on which you will install your electronics, motors, sensors. So choosing the right shape and size of chassis is very important. It will greatly affect the performance of a machine. So always try to choose chassis according to machine's task. For example, let's say in our case, I have chosen chassis such a way that I can have least turning radius as well as distance between my sensors and motors. This will help during turn and sensing junctions properly. I will talk about this in greater detail at later part of this video. But one thing is very clear that you need to have less turning radius, and for that you have to use differential drive, not the servo drive. Here you can see rear view of the machine and notice the distance between two motors. They are mounted as close as possible to make turning radius less. Also I have mounted an additional shelf above motors that overall size of the machine get reduced. The material used to build chassis is same as used in Farber sheds and it is very light and strong. Here you can see side view of the machine and we can easily see the offset between sensor array and my drive axis. Now let's see second component, which is power system, and it is broadly divided into two parts. First one is high voltage system and second is low voltage system. High voltage system is basically for our motors and low voltage system is for all the electronics. Nowadays all the electronic components generally comes with their own voltage regulators, so you don't have to install your own voltage regulator. So all you need to do is make a power distribution board. In this picture you can see the power distribution board. It is important to add electrolyte capacitors which remove spike and surges generated by high voltage consumers like motors in this case from the whole bus, which may cause malfunction of low voltage components. Now let's move to the next component, which is motors. Here there is no particular choice of RPM of motor. You can use medium to high RPM motors. Motors also require motor driver, and I have used L293D H-brick motor driver, which is I think is very simple motor driver. Very briefly its working can be understood from the figure. It is basically 4 switches. When you want to rotate the motor in one direction, you will switch on diagonal switches, and for opposite direction other two diagonal switches. So final component of the hardware is controller. Again there is no specific choice, but choose one with which you are familiar, because this project require a lot of coding. So you have to know all available functions before start writing the program. I have used Arduino Uno for ease of programming, and because of that I was able to focus more on algorithm part. Now let's take second major component, which is sensor and telemetry. It consists of line sensor array, which is nothing but simply multiple IR LED and photodiodes with individual calibration potentiometer. Number of sensors is again not fixed, but go for at least 5, and spacing of the sensor should be such that at a time only 2 sensors can be on. It will make things simple in the algorithm part. Now telemetry is very important to test your algorithm and debug errors. You will get current status of the machine via telemetry. Like in this case you can see in the video of MAZESOLVER, I am transmitting every turn at a junction which is being stored in EEPROM. So it is very helpful to validate your algorithm. You can use Arduino's serial port for the same, but you have to keep your machine physically connected to receiver. So you can use RF transmitter and receiver as shown in this, or more general purpose XB modules, which works really well with very long range. Now let's talk about last major component, which is algorithm. The main logic which will determine the shortest path is LSRB rule. In this rule, at every junction priority is given to left turn, then straight, then right, and last priority will be U-turn or back. This rule can be extended from the simple maze as shown in figure. At first junction priority is given to the left turn, then we have to take U-turn. Again at the junction left turn is available, then again we have left turn, U-turn and straight, which will drive machine to its end. Now we have to decide shortest path, so we have to apply reduction rules. Here we can see that LBL, that means left back left is nothing but going straight, and left back straight is equivalent to right turn. So after making this optimization, my shortest path will be straight and right turn. Now let's test the algorithm in slightly complex maze. You can see a maze here consisting of simple loops which can be eliminated by 3 turn rules, as well as some complex loops which require group of 4 turns to be eliminated. First we have left U-turn left, which is equal to straight. Then we have left U-turn straight, which is nothing but right turn. Then again we have left U-turn left, which is equal to straight. Then we have left turn. Then again we have left U-turn left, which is equal to straight. Again we have straight U-turn straight, which is equal to wrong path, and also we have to remove one additional path, and the whole turn is nothing but a straight. Then we have left U-turn left, which is equal to straight. Again we have straight left U-turn left, which is nothing but straight. Again we have straight U-turn left, which is nothing but right turn. Again we have right U-turn left, which is nothing but wrong path, and we have to remove one additional turn, and whole is equal to right. Then again we have right U-turn left, which is nothing but wrong path. We have to remove one additional turn, and whole system is equal to right turn. And this way we can have shortest path to the maze. You can see actual maze which is used in the project, but please do not start with such maze. I had fairly good experience with differential drive, servo drive and big machines, as well as complex coding during Robocon before this, so I have chosen this maze. It consists of various complex loops as well as parts such as this, just to show the line following ability of the machine. I will upload separate video in which you can see the machine navigating through this portion of the maze. Now the next thing is you have to follow the line during the normal operation. So the line following operation can be done in this way. Suppose assume that this is my sensor array and my machine is a center, so only my center sensor is on. So what I'll do is I will assign error equal to 0. Again in the second position of my sensor I will assign error is +10. Again at third position of my sensor array I will assign error is -10, and same way at extreme positions I will increase the amount of error. And what I will do is I will assign PWM of my left motor and right motor according to error. I will add error in one PWM and I will subtract error from another PWM, so at the end I will get correction of my heading. Now what you have to do is identify the junction, and at junctions what are the turns available, and according to the LSRB rule you have to give priority. Once you identify the junction you have to store each and every junction at your EEPROM. And why EEPROM? Because EEPROM is non-volatile memory, and if you turn off your power then also the turns are saved in your memory and you can run optimization even after switching your power off. So once you have reached at the end of the line, so you can run optimization on the turn saved in your EEPROM. As I have discussed, you have to use optimization in 3 turn block. Like every time you have to check a central turn and one left and one right turn and make a block of 3 turn, and you have to iterate this loop again and again until you find best possible shortest path, and there is no removal of any additional turns from the whole shortest path. And finally you have to update the EEPROM. After optimization your EEPROM will consist only the shortest path which you have to take to reach at the end of the maze.